All right, sixth graders. You should be on the non-contact forces guided notes, which is a document that you guys used last week. And across the document, there's like this line that separates week one from week two. So now we are at the bottom of this at week two. For whatever reason, if you didn't finish week one, which was part of the first week's assignments, you got to make sure that you get that done first. And then email me and tell me that you did it, because more than likely you have a missing grade in there. And I won't know to go back and check it unless you tell me. But real quick, this is where we left off when we were talking about gravitational force and how that affects then the difference between weight and mass. And now we're moving on to magnetic force. All right, so the way that I wanted you to do the work this week is that I wanted you to watch that ed puzzle first. If you haven't watched that ed puzzle yet, I would like you to stop this video and go watch and do the ed puzzle, because I'm going to refer to what the experiment was in that ed puzzle a lot when we're talking about magnetic force here. And for you to truly get what I want you to get out of this video and these notes, you need to go ahead and watch that video first. All right, secondly, some of the feedback I got from last week is that I moved too quickly through these as you guys are trying to type. Especially because they're on two different documents. So I'm going to do a little bit more pausing, or I might even say, before I move on to the next slide, I might just say and give you a reminder to go ahead and pause the video to move on. But this is at your own pace. So of course, you can always just pause it, type, and then hit play. All right. So with that, let's talk about our third non-contact force, and that is the magnetic force. All right, so magnetic fields exist around magnetic objects. So just like all three of these non-contact forces, we have a field, which is the area of influence or the region of influence where these forces are interacting with each other, even though they're not in contact with each other. The field is where they're reacting. Same is true for magnetic field here. Magnetic field lines point away from the North Pole. And so if you look over here, you can see that. There you go, away from the North Pole. And then as obviously you can tell, they move toward the South Pole. So magnetic field lines go away from the North and towards the South. Just like they move for electric field, they go away from the positive and towards the negative. All right, I'm going to pause for a second here. Go ahead, and maybe you should hit pause too and type in those three bullets. Next, we're going to see the strength of the magnetic field decreasing rapidly with increasing distance. And I really hope that as soon as that bullet point came up and I read it, that a red flag went off in your brain or alarms went off in your brain. You're like, well, wait a minute. That is exactly like the other two non-contact forces, because you are correct. That is one thing all three of them have in common. In fact, they have two things in common. I already mentioned the one. They all act in a field. They all have interactions within a field, the region of influence. But then the other thing that they all have in common is that they all decrease in strength the further they get away. And it's all the same, right? It is this curved line. And that's what you should have seen for the electric field lab, is this curved graph when you made a line graph, that it got weaker with distance, and as well as with the gravitational one, weaker with distance. And then if we did one for this one, which we're not going to do, it would get weaker with distance the further you get away. And the reason it's curved is because of what that bullet point says. It decreases rapidly right at the beginning. It's a sharp, steep line. And then it starts to flatten out as you get further away. All right, so that's true for all three of them. So they decrease rapidly at the beginning, and then it starts to taper off or slow down a little bit and flatten out. So we describe those graphs as decreasing at a decreasing rate. And I know that sounds kind of silly using the same terms twice, but that's what's happening. It's decreasing its strength, and the rate at which it's decreasing its strength is also decreasing. It's a lot at the beginning, and it starts to be less of a decrease as you get further and further away. So that's an important thing to remember. And before I move on to the next slide, I just want to reiterate that the two things that all three of these have in common is that they act in a field, a region of influence. They act in a field. And then the second thing is that they all decrease with distance. Okay, they all decrease at a decreasing rate with distance. Okay, all right. Now, the reason we have magnetic force on Earth is because we have Earth's magnetic field. And if you remember all the way back to our first unit of the year when we talked about the layers of the Earth, the reason we have the magnetic field, if you know it, say it out loud to yourself right now. The reason we have Earth's magnetic field is because of the outer core. So the outer core is liquid metal, and it spins around the inner core, and that spinning of that liquid metal creates the magnetic field. So it's the outer core, the liquid outer core causes our magnetic field. Okay. Now, here's what's weird. At least maybe not weird, but a little bit more difficult to understand. You guys know that Santa Claus is up in the North Pole and Antarctica is down in the South Pole. But the magnetic poles, so not the geographic poles, but the magnetic poles are actually different than that. The South Pole of the magnetic field is actually up at the top, at where our geographic North Pole is. So if you're looking at the picture here, right, the South Pole of the magnetic field is up here. The North Pole is down here. Let me move my picture here a little bit. Okay. So it's opposite. It's opposite. Now, if you think about the way a compass works, right? So compasses are magnetic. So if the compass needle is going to point north to the geographic north, that means it must be the opposite pole, which is the magnetic south. And that's how that works. So the magnetic south pole of Earth attracts that north side of the compass magnet so that when you're facing the geographic destination of north, the compass will point to the north geographic pole because it's the south magnetic pole and the opposites attract. Okay. All right, pause the video if you need to. Copy down this before I move to the next slide. So before I go on to a way that we can use Earth's magnetic field with a little bit of electromagnetism and electricity, let's take a second to just kind of make some connections here. When we studied energy in our last unit, one of the forms of energy was electromagnetism. We saw in the Einstein video, we saw Michael Faraday with electromagnetism and all of this, and this idea that there's always a little bit of magnetism where we see electricity, and there's always a little bit of electricity where we see magnetism. So I'm hoping that as you think about these three non-contact forces, you saw a pretty close connection between the factors and characteristics of the magnetic field compared to the factors of the electric field. Okay, so for instance, besides the fact that they decrease in strength at a decreasing rate as you get further away, the same thing we have to make the connection between when you have like charges or like poles or opposite charges and opposite poles. And so we talked about the bridge of attraction and the shield of repulsion when we looked at the electric field, right? If you had like charges, so a positive and a positive, or a negative and a negative, then you had that shield of repulsion there between the charges. As they came out, they never came across and crossed over to each other. They came out and then repelled. Same thing happens in a magnetic field. Like poles also have that shield of repulsion. And the video, it showed a gap between the bars. Unfortunately, it's not, he put them too close together. So you don't see it really well. If you put them a little bit further apart on those pieces of paper, we'd see it a whole lot better. I wish he would have done that. And if we would have done the lab in class, you could have, that's how we had it designed. You would have been able to see it as well. And we would have actually been able to draw in that diamond, like that shield, because it'll happen. Okay, that's the shield of repulsion, because like charges and like poles repel, they push away. So magnetic opposite poles then attract, just like electric charges that are opposite attract. And so there you go. There's the comparison again between between magnetism and between electricity. So now we see those in the same thing. And now you see that bridge of attraction as it goes across. And just like we saw in the electric field lab, the lines, the arrows go straight from one charge to the other. You got to see it again, very small in the guy's video here in his experiment, but you got to see these thin lines that went from one of the bar magnets across to the other, showing that bridge of attraction that the two opposite poles were attracted to each other. All right, so let's talk about then a little bit of electromagnetism and what an electromagnet is. So, an electromagnet is a type of magnet produced using an electric current. And what that means is that when there is electric current flowing through it, so when it's plugged in and turned on, the magnet and the magnetic field then becomes activated as well. All right, so I'm going to pause for a second for you to type that in. Okay, and then you can make them stronger or weaker based off of two characteristics. Okay, and the two factors that affect the strength of electromagnets are the larger core, the stronger the magnetic field. So the core is what's going to be here in the middle, and it's usually some sort of magnet or even some sort of metal. Okay, something that can be magnetic, like a metal. And then we usually wrap around copper wire or coils, and the more coils you have, the stronger it is. So again, we're going to miss out on a lab here that we did where I would give you a nail, a steel nail, and some copper wire, and we would test this by picking up paper clips. Okay, and we'd have that wire attached to a battery. And so with that battery, when you had the wires touching the battery, you could see that you got the end of the nail to be magnetic, and it would pick up the paper clips. And then what we would see is the more times we wrapped the wire around the nail, the more paper clips we'd be able to pick up because it would be stronger. Or I gave you then some different nails that were a little bit thicker, a little bit bigger, or even a little bit longer. And because that core was larger, you would then be able to pick up more of the paper clips as well. Okay. So that's an electromagnet. So go ahead, if you need to pause the video to finish typing that in, pause it, as I'm going to move to the next slide. All right, and then the last slide here has to deal with motors and generators because this is where electromagnetism comes together. Okay. An electric motor, the way they work, and so we're not talking about like a car motor for right now. Okay, we're talking about the things that are like in the pencil sharpener or in the fan when we did our different stations for the energy stations. Those tiny little motors. Okay, they convert electrical energy into mechanical energy, right? By turning the blades to sharpen your pencil, turning this fan blades to get the air moving. And what happens is when we turn those on, the electric current produces a magnetic field. And what that magnetic field does then is converts that into mechanical energy. And that's because literally the magnets will begin to spin around. And that's how the electric motor works, okay? Now, the opposite way that works is that we can then use mechanical energy to somehow produce electrical energy, and that's what a generator is. So when we need to produce electricity. Now, in a power plant, these generators are huge, okay? And we have huge magnets that are moving around these huge, thick wires to produce lots of electricity. And I drew out how a whole power plant works, and we don't need to go through that now. But this was the end part of that, okay? The generator. They have smaller generators that run on gasoline. Maybe even some of your homes, maybe your parents have purchased a backup generator in case we ever lose electricity. That stuff usually runs on gasoline or some type of other fuel that is going to move those magnets to be able to produce the electrical field. Okay, so those are the two different ways we can use magnetism and electricity. And because, again, that relationship between electricity and magnetism, there's always a little bit of magnetism with electricity, and there's always a little bit of electricity when we have with the magnetic field, which is why there's electromagnetic energy. All right. So that's the end of the notes for the non-contact forces for this unit. It's not the end of the unit. We still have to go through forces, which is going to be more next week. All right. So this document at this point, though, should be completely filled out. So at this point, You can either turn in the document if it's easy to turn it in. If it's confusing to turn it in because it's posted back from last week, don't worry about it. I always have access to your documents through Google Classroom, whether you turn them in or not, because I've created the docs for you, okay? But this should be it for those notes. Don't get rid of it. Make sure you remember where it's at, because eventually when we have a quiz or something like that, I will always let you use your notes for this stuff. Since we're doing online learning, all the tests and assessments will be open notes. All right, that's it for today. Good to see you. Take care. Be safe. Have a good day.